Welcome to your notes video about titrations. You should have done a titrations lab earlier this year where you took an unknown acid or an unknown base and you titrated it with the opposite type of solution. So for example, if you have a strong acid where you know its concentration, so for instance like hydrochloric acid, and you know how strong it is, and you add it to an unknown concentration of a base, so like we don't know the NaOH concentration, then you add an indicator there and you are able to determine the concentration of the unknown. In the reverse, you could start with a strong base where you know the concentration, so you could start with like NaOH, and then add it to an acid like hydrochloric acid where you don't know the concentration, mixed with an indicator, and you can figure out that unknown concentration. When you are titrating something, you'd want to know about the equivalence point. And the equivalence point is when the moles of the titrant added are equal to the moles of the acid or base in the solution being titrated. So for instance, for this example up here, it would be the titrant would be the thing that we're adding. So moles of HCl. We're not talking about molarity here. When the moles of hydrochloric acid added are equal to the moles of the thing being titrated. So in that example, it would have been the moles of NaOH. That is the equivalence point. All right, so this slide, a little hard to read. Titrations, equivalence point versus end point. So we're going to talk about the difference between the two. So we have equivalence point first. Like we just said, it's when the moles of the titrant added are equal to the moles of the acid or base in the solution being titrated. The end point is basically when you are doing the lab, it's as close as you can get to the equivalence point. So the end point is like an experimental type of thing. You know that the equivalence point exists, and you are trying to get as close as you can to that with the end point. So it's pretty much where you stop the lab if you're not using probeware. It's when you see the indicator change colors. So there are three different types of titrations. You could have two strong substances. You could have a weak acid with a strong base, or a weak base with a strong acid. Here is an example titration curve when you have two strong substances added together. So you start off with your initial concentration and of the unknown, and you've got its pH, you're able to read that. And as you add NaOH to the solution, the pH gets more and more basic, which makes sense because it's sodium hydroxide that makes it more basic. And once you reach the equivalence point, which is halfway between this very straight line here, that's when you know you have moles of hydrochloric acid are equal to the moles of the titrant added. They're telling us this is NaOH being titrating hydrochloric acid. Here we have the reverse, the titration curve of a strong base NaOH with a strong acid, hydrochloric acid. So they're tracking as we add hydrochloric acid, the pH actually drops, and at the equivalence point again, the moles are equal to each other. And you can use that to solve for concentrations. Now notice when you have a strong acid titrating a strong base, or the reverse, what is the pH at the equivalence point? The pH is 7. Again, this is assuming everything's at 25 degrees Celsius. Pretty much everything we're doing, we're assuming that. So here we're going to say that again. The initial pH for a strong acid is close to 1. When it's further from that, the further you get, the weaker it is. And then you keep adding your titrant until eventually it reaches the equivalence point, which is a pH of 7 when you have a strong substance mixed with another strong substance. Okay, well, what if you have a weak acid with a strong base? So what's a good weak acid? This could be an example. Okay, so Here we have our end point, like we're doing this lab ourselves, and we measure, okay, this is when the color of the indicator changed. And so that's our end point, which is hopefully the equivalence point as well. Something else that's useful is here at this point, when you are halfway across this flat part of the line, that's when the pH is also equal to the pKa of your weak substance. In other words, the negative log of the concentration of your hydrogen ions at this point is equal to the negative log of the Ka of your weak substance. That is also useful. Okay, well, here it is again. So there it is, equivalence point. Now in this case, when you're titrating a weak acid with a strong base, when the moles of your weak acid are equal to the moles of your strong base, is it going to be neutral, like when you had a strong acid and a strong base? No. If you have an equal amount of weak acid and strong base, then that strong base is going to take over, and it's going to have a pH that is in the basic range. So that's why here the end point, even though the moles are equal, that does not mean it will be neutral. This is above 7. There's 7 down here. Something else that's helpful when you're reading these graphs, we know that weak substances can act as buffers. That's something we learned in the previous video. And the buffer zone is here where you can see the weak acid is resisting being made basic. And once it hits this like turning point, then we know, okay, we have probably run out of weak acid, and the strong base is now changing the pH without anything holding it back. So this would be considered the buffer zone. All right, so here is now a weak base, so something like ammonia, plus a strong acid, something like hydrochloric acid. Oh, I just made those up, and look at that, they match the graph. I'm so special. All right, so we started off with something that is basic, and oh, it's resisting the change, it's resisting being made acidic. There's the buffer zone right here. And eventually we run out of our weak base and it becomes acidic very quickly. Here's our equivalence point. Here is where pH of 7 is at. So again, the equivalence point is when the moles are equal. So when you have a strong acid titrating a weak base, your pH should be less than 7. It should be acidic because we've got a strong acid with a weak base. Something that's helpful here in this buffer zone is this little phrase right here: the acid is equal to a half of the base. We have a graph coming up. I think it's the next one that'll make this a little more clear. Yeah, okay. Don't panic. We're going to get through this. So here is a polyprotic acid. So it could be, H3PO4. We know H3PO4 goes through many steps. First it'll become H2PO4, minus, because it released one hydrogen. Then it'll release another hydrogen, and it'll become HPO4 2 minus, and then it releases its last hydrogen, and it becomes just plain old phosphate. So here are all the different steps. We have 3 different curves going on here. So let's first look at the equivalence points. There are 1, 2, 3 equivalence points. This is when the moles are equal to each other. So here we have moles of NaOH are equal to the moles of the first ion that is released. So here's the first ion that's released. Here. Then we get to our second equivalence point, where we're dealing with our next ion, and that is when our HPO4 2 minus moles are equal to the moles of the NaOH that have been added. And then we have our third up here. Okay, then we have half equivalence points. Half equivalence points, which happen at the other halfway point on these curves. So here, that is when, so you can look up at my original little flow chart here. What we have originally is H3PO4 over here, and it is becoming H2PO4 minus. And at this first half equivalence point, the concentrations are equal to each other. Right here, it is halfway through turning into the new ion. Then when you get up here, same type of thing. H2PO4 minus is becoming HPO42 minus, and halfway on this line, the concentrations are equal to each other. It is halfway through becoming the new ion, and finally HPO42 minus. This one's a little harder to read, but PO4 3 minus there. So here we are halfway where the HPO42 minus concentration is equal to the phosphate concentration. So these are all useful points on your graph that we're going to practice using in our notebook. So now we're going to move on to talking about indicators. So here's a polyprotic acid again. How many hydrogens are released on this one? You can count how many curves there are. There is one curve. Here, I think my pen might have disappeared there. There's one curve, and then here's the second curve. So there are 2 hydrogens that are released on this one, carbonic acid. And let's see. So we know at this point right here, we have lost, or we have converted all of our original acid into the first ion. And then we know at this point up here, it has been converted again. And these little boxes right on here, the colorful, pretty ones, they show you how indicators can help you see where different things happen. If we had used thymol blue indicator in our solution, we would be what would be the word indicated? It would be indicated to us when the pH reaches this range. We could see, oh, at about 8.3, it's going to change from yellow to blue. Well, that's helpful. And if we used phenolphthalein instead, that one will show us when we switch from around the 10.3 mark, which is around our second equivalence point. This one's around our first-ish, around the first equivalence points. You want your indicators to match equivalence points as closely as possible. So here's a little slide about how they work. Acid-base indicators are weak acids. That's what they are. So here we have hydrogen and I believe it's indium, I might be saying that incorrectly, where it starts off as one color. However, when all of the ions are released, we have a different color. So these color changes that are experienced by different indicators occur over different pH ranges. You must select an indicator that changes color at a pH that is as close as possible to the pH at the equivalence point, because the equivalence point is the most useful part of those graphs. That's when we can say, oh, I know exactly how many moles of everything I have, and I can use that with stoichiometry to figure out my concentration. So just a special note, sometimes only the pKa of the indicator is given, and that's okay because pKa is basically the same as pH, so not a big deal. Don't panic. If you see pKa, you don't have to do anything very different. So here's a range of pHs. We have methyl orange, methyl red, bromcresol purple, bromothymol blue, phenolphthalein, and alizarin yellow. Some of the more commonly used ones are phenolphthalein and bromothymol blue, although the others are also useful. So here's a visual version of that. You can see that if you're working with a substance where you expect the equivalence point to be around, like between 0 to 2, methyl violet would be helpful. Thymol blue has a really big range here. Methyl yellow, you'd want to work with something that is going to change somewhere in there. Let's look at bromothymol blue. We want something that's going to change somewhere inside of here. So something that is going to have an equivalence point at a pH of 7. We'd probably want to use bromothymol blue because that one, it's centered around 7. Phenolphthalein, for that one, we could see its range is around here. So that one, maybe something that's going to be more basic around its equivalence point. Phenolphthalein would be helpful. So here's an example where if we had used phenolphthalein, then its color change interval is inside of this range, whereas methyl red, its color change interval is at a different range. So if I was working with like this blue substance here, its equivalence point falls within the methyl red range. So for it, we'd want to use methyl red. However, the red substance, its equivalence point is closer to the phenolphthalein area. That one doesn't look perfect though, so we might not have wanted that one. Something that falls in this white range might be better. Okay, so what indicator would you use when titrating hydrochloric acid with an equivalence point at pH of equal to 7? Oh, there's a spoiler. Okay, well, the answer to this would be bromothymol blue. So let's see if that makes sense. Let's go back to this slide. So if we're mixing if we're mixing hydrochloric acid and sodium hydroxide, we know that the equivalence point is going to occur at a pH equal to 7. So looking here, oh, well, a pH of 7 lies right in the center of bromothymol blue's range, so that's why we'd want to use it. Okay, well, what about if we're titrating acetic acid with NaOH, where they're telling us the pKa is equal to 9.1, and like we said earlier, if the pKa is 9.1, the pH is also about 9.1. So go back and look at your list and find, okay, which one has 9.1 lying somewhere in the middle there? And it looks like phenolphthalein is our winner. Winner, winner, chicken dinner. So if we are mixing a weak acid with a strong base, where we know the pH at the equivalence point is going to be equal to about 9.1, then phenolphthalein is what we'd want to use because it'll change color around the equivalence point. Okay, oh no, oh, that's an answer. Okay, well, that's okay. We have a solution of barium hydroxide that's being titrated with sulfuric acid. So I wrote out the molecular equation. It's not net ionic yet. Now we're asked to write the balanced net ionic equation for the neutralization and the precipitation reaction. We're just going to write one equation that works for both. So for these, you need to know, okay, what is soluble and what is not. So, well, we know that these guys are strong base, oops, and here we have a strong acid. Think back to your solubility rules. Does barium sulfate dissolve? Is it soluble in water? This guy is insoluble. And water, we don't break it into its ions, so I'll leave it as it is. So when I rewrite it, I'll write Ba plus 2OH plus 2H plus. Why am I breaking up these bases and acids? Why am I not leaving them whole? The answer would be because they are strong substances. So strong acids and strong bases, you can break them into their ions. Barium sulfate, however, is insoluble, so I will leave it as it is. And my waters, I will leave as they are. So here I've got it balanced. That's good. Are there any ions that I can cancel out? I don't see any. I'm going to label what is aqueous and what is not. Here we know this is a solid and that's a liquid. Okay, so we're going to look at this conductivity chart and it's going to help us figure out it's similar to how you'd use a titration. You can use this to figure out conductivity and when different things are equal to each other. So let's go on to the next slide then. So we know that the conductivity of barium hydroxide decreases. So here it is. This is initially barium hydroxide. So it decreases as the volume of sulfuric acid, it changes from 0 to 30. So we're talking about from here to here. And they're asking us to identify the chemical species that enables the solution to conduct electricity as the first 30 milliliters of 0.10 molarity sulfuric acid is added. Okay. So when you're reading a conductivity chart, what's important to know is right here on these charts, it's like the equivalence point. The moles of our substance that's being titrated are equal to the moles of our titrant. So before that, like let's say over here, do we have more barium hydroxide or more sulfuric acid? Here we have more barium hydroxide because we are slowly adding more and more of our titrant. Okay, so if that's the case, which one of these is allowing us to conduct electricity? Our barium hydroxide is. As we add the sulfuric acid, it's all getting used to neutralize whatever barium hydroxides it can attach itself to. However, there isn't enough sulfuric acid to neutralize all of the barium hydroxides until you reach this equivalence point. So we know that this guy is the only one that's producing ions that are actually available to conduct. Can a solid like barium sulfate conduct electricity? No, these do not conduct. So it's only the ions that are being produced that can conduct. All right, well then the conductivity of barium hydroxide decreases as we go from 0 to 30. Why is it that it decreases its conductivity? Why would that be? Well, we know right here that the moles are equal to each other. Moles of base equal to moles of acid, which means as we're getting closer and closer to this point, they're getting closer and closer to being equal and completely used up. And down here, right at this point, do we have any free ions? Not really. They're all being used with each other. But here we have some free barium hydroxides still. This one we have tons of free barium hydroxides, and as we get closer, the sulfuric acid starts attaching itself to them, lowering conductivity until you reach this point. Now, why is it that the conductivity increases as you go past that point? We know earlier the excess barium hydroxide allowed electricity to be conducted. However, on the other side of things, all of the barium hydroxide has been reacted with, and now we just keep adding sulfuric acid. It's like overkill. And so on the other side of things, now we have excess sulfuric acid, and we know that is strong, and so it splits into ions, and so this now is allowing us to conduct electricity. And that's how you can use conductivity charts in a similar way to how you would use a titration graph.